The demise of the static timing verification. The chip industry traditional time is increasingly dependent on factors. Can static techniques continue to deliver the necessary result? Maybe. The chip industry traditionally has relied on the margin to help them mitigate the timing problems, but an increasing array of factors now influencing timing. Can static timing analysis evolve to address these problems? Static time verification, STA, was the cornerstone technology for the consistency of the register transfer level ultra resolution. It shows that a functionality would not be impacted by timing so long as the longest combinatorial path would settle within the clock period. During the 19th, data implemented adding up the numbers of gates, multiplying by the gate delay, and compare against the clock period. Then wires started to impart greater delays than date, and the calculation becomes dependent on the place and route. That drove adoption of physical synthesis, but the delay calculation was still fixed. There are many things that impact timing, and most of them are activity dependent. To make things even more complicated, the activities will be impacted over the order of the magnitude of time, ranging from the nanosecond to operational time. Until the establishment of the state, all design had to be simulated at the gate level. That is not scalable, said Wei Li Tan, director of the product management of Demise in the digital industry software. We were not able to run full custom simulation or transistor level simulation on design back then, and we certainly can't today. Designing are getting better, larger. There is an increasing number of effects that have to be taken into account during the digital flow. Having said that, STAB has been evolving and will continue to evolve to address these new impacts that are coming. The alternatives that I have to custom time everything, and that's not scalable. That's not impacting everyone today. Most people take just general margin, said Mark Dewiner, director of product marketing and analysis, not part of synopsis. With the general margins, you assume that every gate could be up to this much voltage derated, and hence every gate could be slowed down by this much. This may be an expensive assumption to make across the entire design, when in fact it's only a tiny fraction of the gate that actually experience a voltage drop, anywhere near that big. You make everybody pay for the sins of you. Static tools are generally not activity-driven. The whole beauty of ST is that it is activity-independent. There are many factors to consider. We use a classical method, this which is put in margin for unknown problems, said Andy Hennig, head of the Department of the Efficiency Electronics for the IIS Engineering of the Adaptive System Division. Not everything we do is that advanced today, but I expect it will become the necessary at some point. It should really relate to the product. Which type of product, to what frequency is it intended to operate at, and so on. That can make the decision very hard. It is a balancing act. When the silicon first comes back from the fab, it tends to fall short in operational frequency, said Ansis Swinen. And while margins are considered to be safer, and you won't be miss anything since you've seen the worst of it for everybody. That is not always the case. You might find that with that detailed analysis, you have missed the worst case. It all depends on the risks that you are willing to take. There are several factors impacting timing. The shortest time scales is IR drop. The medium time scale includes things such as summer, while aging is the longest time scale. These are all activity dependent on new manufacturing technologies such as 3D stacking are adding things like stress-induced timing. All of these needs to be taken into account if static timing analysis is to remain relevant. A small time scale. IR drop happens when transistors demand more current than can be applied at a given moment in time. With a newer node, you get more transistors crammed into the same area, said Sweden. In addition, these transistors switch more quickly, which means that you have more intense, sudden current draws. You get more change of the current over time, the IDT, and that current has been sourced locally. While there are capacitors of chips, from the transistor point of view, that is far away, and there is so much resistance between it and the capacitor that the current will never get to you in time. If the current cannot come, the voltage will drop. It is not localized problem and hard to solve using the capacitors. This has been a problem for advanced nodes for the past 10 years. Customers understand the impact, but they are already designing for it, said Manoj, the Palalati, senior staff product manager at Synopsys. IR is highly dependent on the vectors. So having knowledge on the AutoCADE impact that is going to be caused by different factors needs to be considered as part of the IR STA. It does require an extra analysis step. However, most tools have an instance-based IR drop static timing analysis, such as TOMS. The tool is given information about the IR drops for each instance of the impact. They calculated based on the voltage drop going into each instance, and the data time live contents for information that tells the ST tools how the logic blocks are going to behave based on the IR drop. Each of these gates needs to have each performance rated based on the voltage. You need multiple live rails characterized for multiple voltages, and then they interpolate between those to find the performance of the gate at a specific voltage, supply voltage. Said Sweden. Given the voltage values, ST tools can do a regular analysis. It is just changes the library information of each of those gates based on later voltage, but it's a lot of information, and it's typically just only done for crucial paths or time-sensitive paths. Because the voltage drive is activity dependent, there is a risk that the worst case is not considered. Some designs have experienced significantly more voltage drop than expected, said of Sweden. As you crack update the speed, at some point you are getting to have a dynamic voltage throughout the choke of the performance. A result in not quite being able to achieve your supposed target performance, and it's difficult to undetect it or escape the voltage drop conditions. Medium and long time scale. An energy problem is that heat, which will become a major contributor to a delay when the 3D stacking becomes more common. So far, it has been a problem, said the Synopsys Palapati. Customers are dealing with it by setting a uniform rate that applies to whole die, but that is changing because of HHP designs. When you have multi-die stacking, now the impact of the temperature is not uniform across the die. If you go with a single rate, the single margin, either you are missing something or you are over designing. That's where the summer aware stage becomes really important. Double impact are being incorporated into increasing arrays of tools. Even large chips, you have the temperature gradient set Sweden. Traditionally, press and lot tools have to go to the point of actually measuring temperature. They are used as power density as a proxy. Power density is the amount of time being used by the gauge, and you count them up in a scale as given a number. It's a relative measure of how much power is being used to produced in each little sector. Areas that have a higher power density, you have the higher temperature, and you can differentiate the power of the chip being at a different PVT corner. Aging and the manufacturing variation started to become the concern about 10 years ago and is highly important to industries such as automotive, where the product life cycles are longer. We started out by putting in a flat D rate, said Tom. I'm going to add a XS percentage rate just to do margin. The variation that's going to happen. That was too pessimistic. It evolved first into owner variation setting and later evolved into instance-based. For instance, the tool will calculate impact variation. The live evolved to be more granular in its approach. It's not on the side feature, which is more pessimistic. Aging takes a similar approach. Customers price set margin for a whole design to get a aging, but with the process nodes coming down, and with the supply voltage coming down, and margin is leaving something in the PPA side, and usually reveal the performance table, said the party. So that we are doing a true negative native aging analysis that compute the aging impact on us timing, the taking the different BTIs, different activities, different time horizon, and we can do negative and native aging analysis. This is becoming a mainstream application. As the industry continues to adopt 3D stacking, many of these issues become worse. Thermal density becomes larger than a set time. Code optimization comes into play. For example, how do you optimize logic between the two agent chiplet at the at the very basic level? It's still LTA. Now we have even more factors to take into account, as they will have to evolve to be efficient and more granularity. Design flows have to become more aware of timing, all the way from the floating planning to the final route and the sign-off stages. This will become necessary steps before the third-party chiplet can thrive. As you can add the chiplet designs, you are going to able to time across the old chiplet, said Joe Davis, a senior director of the product management at Demise, digital industry software, is going to behave slightly differently depending on how it's integrated, whether it's integrated onto a silicon substrate or organic substrate, or if it's sandwiched between the different things, but you've got the interface and handshake between everything, and this enables to make it a solvable problem. Future innovation will occur to bring in more those intelligent challenges, at at a, at a time, one at a time. The manufacturing process also introduces new issues. Stress is something that is emerging, said Palapati. This is not a prominent as IR, thermal, as aging today, but it will be in a year or two because of multi-die and HBM stacking. The stack generates so much heat and warpage that a stress will become important for those markets. Backside matter also creates complications. When you have a heat coming from the bottom, it will impact very non-uniformly. If it is 10 or 20 difference between the hot and cold points, that may be measurable. If it is more than, you need to model it because it will impact timing. It all becomes a little complex. The problem is how do you assign which gate is at which temperature, at which activity, and which age, said Sweden. Putting all that information together, the drive timing, that's where the problem is. It's not the final calculation that's sure. It shall assemble all the necessary information to accurately capture the variation across the chip. Methodologies. There is a standard methodology that everyone uses. It is very dependent on the markets you are addressing, the technology nodes being used, and the degree to which frequency is under pressure. We learn from all the tape out that from 4 Heineck for yield, you get a good feeling about what is possible and what is possible and what is impossible. A field text our product is very similar regarding the frequency and technology. You have a good knowledge that you can reuse. But if you switch to new technology, you may need one or two rounds to learn more. You can improve it by the lead design, or you will the next design. If you are designing a product at a high volume, many companies do a respin to improve the yield when you have a product of smaller volume. You may not be that aggressive with your margin. Companies can progressively tackle the problem depending on the level of the problem they expected. If you get a digital implementation flow, it's an homogeneous flow set time. There are stages where you are making broad stroke, like a synthesis placement, then there is a stage toward the end where you are doing issues. You can do a lot of fine tuning. There is a spectrum of you where you use delays and the broad stroke. And then the day when you get a toward the latter part of the flow, you can build in a lot of granularity. Instance-based C issues and instance-based time analysis. Help is required to ensure the voltage span in the right places. We have something called graph-based analysis that look at the full design, said parity. It gives you about to a whole timing. And then the worst and the critical path that you can do more exhaustive path-based analysis, PBA, that gives you more details and highly accurate local analysis for both critical path timing and the sensitivity in terms of IR. For example, I can have a path that is highly sensitive to IR. Those are important to annotate back to a IR tool, get the IR impact. Then do that analysis again for those paths. All of that needs to be considered early. This is where the architect earn their money, said James Davis. This is why floor planning in chip design is such critical aspect. There are trade-off between getting higher performance by putting things closer together because it results in less delay, but it also creates more heat, which is going to cause it to slow down. There is a balance. Many of the factors are vector depending, and while these may be useful for analyzing IR drop, that approach is then less realistic for thermal and aging. You can provide factors as an input, such as parity. You can take a FSDB file that show activity for each node, and then do activity propagation for full design. Based on that, we do a quicker power analysis to get the time impact. We consider that a part of the aging analysis, but it's computation intensive. Another approach is applying more static ways of solving the problem. You can apply a toggle rate or a static probability for a whole design, which is based on the designer's expertise. Solutions have balanced across the computational cost. As you get to very large systems, you have to use a vectorless approach, said Davis. But a vectorless approach is going to tell you everything, anything about when something is gonna happen. Where my where are my hotspots? When are my hotspots? Is this floor plan going to work? Early simulation becomes more critical from a typical standpoint that is challenging today because a lot of data simulation does come until late in the process. Shift left. How can I get a good enough model to be useful? While I'm getting to the point where it's really known, I need data early that is perhaps not perfectly accurate, but useful information. Not all parts of the design may warrant such deep analysis. Some companies may wanna be very aggressive for the CPU block because that's where they can make a lot of difference in terms of getting the whole chip performance maxed out, said Palapati. They'll spend a lot of time tweaking that margin as much as they can for that block. For other blocks, not as much. The ROI is not significant. The value varies based on the project cycle, the complexity, the risk tolerance. It also varies based on the application they are doing. If the risk of the escape keeps you up at night, Davis offers another alternative. One technique that has picked up the stream is putting IR draw sensors or temperature sensors in that die to do dynamic correction of the clock as you detect excursions. That they really changes your perspective on what you're designing for. If you have a safety valve that says, if there's an IR draw excursion that has potential to create race conditions or performance issues, I'm going to lower my clock until I get past that. And then I'm going to recover. Conclusion. While there are many added to challenges, they all can be solved with enough computation. The report of STA's deaths are greatly exaggerated, said Davis. There's always scope within the switch applicable. It is about defining the scope, and as we incrementally add capability, different voltages, different temperatures, or different process corners, you can analyze the defect, time, and worst cause propagation. And also in the worst case, I'm going to arrive before this, and a worst case, and I'm going to switch this time. If this the time, you can always define as an area well that's going to be invalid. Going to be valid. EDA companies are making rapid progress. This is really interesting time to the sense that the complexity is increasing and so many new effects are coming into play, said Palapalati. AR, aging, thermal, stress. These are extremely important for accuracy and margin reduction. The other side of the problem is that a growing number of chiplets, the growing number of areas, the growing numbers of cell instances in each die. It puts strain on SD tools in terms of compute needs to the TAT needs a lot of innovation is going into this area to solve these problems. Today I read this article, the demise of the static timing verification. Thank you for your time. See you next time.